The next operation we're going to talk about is the curl of a vector. So the curl of some vector field A is the rotational vector with magnitude equal to the maximum circulation of A per unit area as the area tends to 0. And as I've noted here, we are operating on a vector and our result is a vector as well. And the direction of this vector is normal to the area when the area is oriented for maximum circulation. So as with all of these operations, this is just sort of a big wall of text, awkward bunch of words, but hopefully we can simplify things here in a little bit. But let's start by writing a mathematical equation to sort of represent what is written here in words. So we can say the curl of A is equal to del cross A. So we're using our vector cross product, and that's going to be equal to the limit as that delta S, our surface, is going to 0 of, now we're going to have a line integral along the closed path L of A dot dl, so we have the circulation of A around L divided by that delta S, and our result is a vector, so we need to have this in a direction, so this is our maximum value, and this is going to be in the direction of some unit normal vector. And so a couple sort of things to qualify here is that this delta S is the bound area, so our area bounded by L. So area bounded by our curve, our line, our contour, L. And this u sub n, of course, over here is our unit normal vector. So unit normal vector. And we can determine the direction using our right-hand rule. So I've abbreviated that RHR. And so we'll talk about how to do that here in a second. One other thing I want to mention really quickly, though, is that in some cases you might see, instead of curl A, you might see rot A. So some people use that notation instead. But most of the time you'll see this curl A. So let's talk about, as we have with our other operations, sort of a physical interpretation. What does this actually mean as opposed to this big sort of unwieldy definition here? So essentially the curl of the vector field A is just talking about how much it rotates at some point. So curl of vector field A at point P, so we need to talk about it at some particular point, is the measure of how much the field curls around P. So measure of how much the field curls around B, or point P. Okay, so sort of similar to what we did with our divergence, we can draw sort of a couple simplistic cases. So let's say we have some point P here, and around P maybe we have some vector field that's moving in this direction. So if we have something like this, then we're going to have some non-zero curl at P. And so using our right hand rule, what we would do is we would put the fingers of our right hand in line with these vectors such that they can curl in towards our surface that is enclosing P. And we see that the thumb on our right hand is then pointing sort of up out of the page. So we would say curl at P is out of the page here, and of course non-zero. So curl at P out of the page, and let's just put in parentheses here that this is a non-zero curl. Now alternatively, if we had a point P and these vectors did not have any curl around it, so maybe they're just passing straight through, something like this. So if this is, and so I should have labeled this if this is our vector field A. For this case over here on the right, we would have zero curl at P. And so another sort of analogy that might make this easier to visualize is we can think about an object floating down a river. So we could describe divergence, gradient, all of these things for our object floating, but if it's actually rotating on the surface, we could also describe a curl of that object as well. And so what we would see is that curl vector would be pointing either up out of the river or down into the river, depending on the direction that it's rotating in. All right, so let's look at sort of our more detailed definitions of our curl for all three of our coordinate systems. And so I'm not going to show a lot of details about how we sort of prove that it is equal to the cross product of del and our vector field. But if you want to see more details on that, you can look on pages 82 and 83 in the textbook. So let's start with our Cartesian coordinates. So in our Cartesian coordinates, so it turns out that it's true that we can do del cross A in any of our coordinate systems, but that determinant's going to look a little bit different depending on which coordinate system we're in. So in our Cartesian coordinates, we have u of x, u of y, u of z. For our second row, then we have our del operator, which is our partial with respect to x, our partial with respect to y, and our partial with respect to z. And then our third row of this determinant is going to be our vector field A. So we're going to have some x component of A, some y component of A, and some z component of A. And so if we evaluate that determinant, we get an expression for the curl of A. So del cross A equals, so we have partial of z with respect to y, partial of A sub z with respect to y, minus partial of A sub y with respect to z. And that is in our x direction, plus partial of our x component with respect to z, minus the partial of our z component with respect to x in our y direction. And then finally for our third term, we have the partial of y with respect to x minus the partial of our x component with respect to y. And that's in our z direction. Again, this is something that you don't need to remember, but just something that you can reference. Something that can kind of help you recognize that it's in the correct form maybe a little quicker is, of course, we notice that this term multiplied by our u of x, so in our x direction, only has things concerning z and y. So we have partial of z with respect to y, partial of y with respect to z. Of course, we can see our z component. We're never taking the partial of that z component with respect to z. So there's sort of little tricks that you can do to help sort of memorize or at least recognize the correct form. But again, you don't need to memorize this. And there's actually a handy reference table with all of these equations in the back cover of your textbook as well. Okay, so that was for our Cartesian coordinate system. So let's take a look now at our cylindrical coordinate system. And so as we've seen before, unfortunately things just continue to get more complicated as we get into these other coordinate systems. So we can, let me sort of copy this to save some time here. So we can use the same basic definition of our cross product, but now we're going to be changing some things slightly. So first of all, we know that this is no longer going to be our x, y, and z components, but rather this is going to be our rho, our phi, and our z component. We're also multiplying this phi component by rho. And now instead of these partial derivatives with respect to x, y, and z, we have partial derivatives with respect to rho, phi, and z. And based on some of the stuff, the derivation that we didn't look at, we also have this 1 over rho term out front. So if we evaluate this, we get our expression for curl in our cylindrical coordinates. So curl of A is equal to, so we're going to have 1 over rho times the partial of z component with respect to phi minus the partial of our phi component with respect to z, that's in our rho direction, plus the partial of our rho component with respect to z, minus the partial of our z component with respect to rho, and that's in our phi direction, plus 1 over rho times the quantity of the partial of, and then in parentheses we have rho a phi with respect to rho. And so I just want to point out here that this is a case where you would want to multiply that phi component by rho before taking the partial derivative. So then we subtract from that the partial of our rho component with respect to phi, and that's in our z direction. So that's our expression for curl in our cylindrical coordinates. So then finally, let's come down here to a new page to do our spherical coordinates. So for our spherical coordinates, same basic sort of format here. We're going to have another term out front. In this case, it's going to be 1 over r squared sine of theta. And we're still going to have to make some changes in here as well. So again, this is no longer dx, dy, dz, but instead we're going to have r, theta, and phi. And we're going to have to make some changes in our bottom row as well. So we're going to have here, and so let me actually, well, we'll see if I can fit it in. So we're going to have a sub r, we're going to have r times a sub theta, and here we're going to have r sine of theta. Just write that a little clearer here, r sine of theta times r a phi. So we get something that looks like this. So again, we can evaluate this determinant, and we're going to get the messiest one yet. So our curl of A in spherical coordinates is equal to, so we have 1 over r sine of theta times this whole quantity of the partial of A phi sine theta with respect to theta. So again, this is a place where we would want to multiply by that sine of theta prior to taking our partial derivative, minus the partial of our theta component with respect to phi, so that is in our r direction, plus 1 over r times 1 over, and so actually let me just move this down here and we'll do one sort of component per line here. So we have 1 over sine of theta So that times our partial derivative of our r component with respect to phi minus the partial of, in parentheses, r times our phi component with respect to r, all of that in our theta direction. So again, here's another case where we want to multiply that by that r prior to doing that partial derivative. So then finally, one more term, we have 1 over r times the whole quantity of the partial of r times a sub theta divided by, with respect to r, minus our partial of the r component with respect to theta. So you can see even just writing these, and that's in our theta or our phi direction, even just writing these is kind of difficult. So it takes a lot of time to sort of do anything with this. And you might be asking yourself, well, why would we even bother with equations that are so complicated? And as we're going to see later on, it works out in certain problems when we have symmetry, for instance, spherical symmetry. We're going to have a lot of these terms going away or canceling out, and it's going to be a lot easier than if we were trying to sort of brute force that in Cartesian coordinates, for example. In the next video, we're going to come back and we're going to talk about some properties of this curl.